Hi, everyone. Welcome to today's webinar, Digging into Details, a deep dive into passive building detailing, which is the latest in our Road to PhiusCon Education Series hosted in partnership with Phius. My name is Miranda Wright. I'm the Education Engagement Manager at Illinois Green Alliance. I want to thank everyone for joining us today and getting into the details of detailing. For those interested and who may not know, PhiusCon this year will be hosted in Milwaukee. So that is why we have created this series to drum up some conversations and prep for this Midwest conference. Link is in the chat now to learn more. Everyone has been muted upon entry. We'll have a QA session at the end, and we'll start using the hand raising function to unmute and have more of a conversation as we go along. Quickly, I'll do an intro of who Illinois Green is. We are a membership-driven nonprofit that advances sustainability in the built environment to ensure greener and healthier communities across the state. Through our collaborative initiatives, innovative programming, and advocacy efforts, we've amplified the voice of the green building community to position Illinois as a leader in sustainable building practices. Our members represent every sector in the building industry, from architects and engineers to building owners and construction professionals. You can learn more about membership, check out upcoming events, and learn how to get involved by visiting our website. Link will be in the chat. And before we get started, we want to thank our incredible sustaining sponsors for their commitment to our mission. A special thank you to our gold level sponsors, ComEd, USGBC, and Sloan. If you and your organization want to commit to advancing our vision for a net zero future in Illinois, visit our sponsorship page to start the conversation today. And now let's get started with the program. I'd like to introduce you to our speaker today, James Ortega. James is the Certification Program Director at Phius. He has been with Phius since 2014. He's the leader of the Building Certification Review Team, an instructor for Phius Certified Consultant Training, holds a Bachelor of Architecture degree from the Illinois Institute of Technology, and is a licensed architect in the state of Illinois. Take it away, James.
Thank you, Miranda. Hello, everybody. My name is James. I'm going to share my screen now so I can talk to you guys about what you're interested in. So yeah, we are going to go over a few things today. I'm going to give a really brief overview of what Phius is, what passive building is, basic overview of passive building principles, and then get into some actual, detailing and stuff like that in terms of what we're looking for. So Phius is a lot of things. We are a nonprofit organization based in Chicago. We have a pretty far-reaching mission, though. We are trying to make passive buildings mainstream, reduce energy use of buildings across North America, basically, is our goal at this point. But we teach professionals, so we have consultant training for architects and engineers. We have a builder training. We have an on-site quality assurance training for raters and verifiers. And then we also train trainers. So I'm a trained certification trainer for Phius who can teach CPHC training. We certify products. So we have a window program where our goal is to basically pull together performance data in a kind of universally applicable format so that teams can make apples to apples comparison on the performance associated with different window products. And then our big piece that I work on personally is our certification program for buildings. So we have a certification standard. It's called the Phius Climate Specific Passive Building Standard that we've been working on and certifying buildings to for quite a long time now. So I'm going to talk about the details associated with some of those buildings that we have certified. And then our last piece that we work on is we have a membership group called the Phius Alliance. And we have a Chicago chapter. We have a couple of other chapters spread out throughout the United States as well. So what is passive building? What is Phius? A lot of folks may be familiar with passive solar from the early 70s. Maybe you're familiar with passive house in general. But we are trying to rebrand, trying to go towards passive buildings because we don't just certify single family homes. We don't just certify small buildings. All of these projects that I'm showing on this image are projects that have been certified to our standard. So we go from kind of high-rise multifamily buildings, non-residential projects, And then we still do single family homes as well. And then a big part of our climate specific standard is that we're trying to develop standards for all of the different climate zones across the United States and Canada. So we've got a project in the upper right corner, which is in the Sonoran Desert. Got a project in the bottom right corner, which is somewhere in Colorado. The big towers in New York. So we got projects all over the place. In general, what we're trying to do with passive building as a strategy as a whole is to reduce our energy use both in the peak capacity, so how big your mechanical system needs to be, and in the annual energy use of the building. So the graphic on the left is kind of showing a curve fit, and it's showing basically that heating energy is the energy use under that curve. So most of the heating in this particular graphic is happening in January, December. This is probably a colder climate building. Most of the cooling energy obviously would happen in the summer. And then we've got this base load of lighting, appliances, and domestic hot water, which aren't necessarily influenced by the climate. So in a typical building, those peaks are very high, right? You don't have a lot of insulation or good air sealing or good windows to help you reduce the annual usage as well as the peak demands. So in a passive building, the goal is to introduce passive strategies like air sealing, better envelope, including air tightness, insulation, really good windows, and using those passive strategies to reduce the peak load, which will help reduce the overall size required for the space conditioning systems and reduce that annual energy use as well. So again, annual energy is the area under that curve. The peak power is the point at the top of the curve. So passive building does a big step in both directions of helping reduce peak loads and annual energy consumption associated with space conditioning. So passive building principles, I've went over them very quickly before, but we've got kind of 6 big pieces that we like to look at into 3 categories. So thermal control is very important, air control is really important, and radiation control is important in our buildings that we care about here. So in the thermal control category, we got high performance insulation and trying to eliminate thermal bridges. Bridges are really good in a lot of places. In a thermal aspect, they're not. Thermal bridges lead to issues with comfort, they can lead to condensation risk, and they can lead to energy loss as well. So this is when a highly conductive material goes from the inside of your building all the way to the outside, and heat follows that path a lot more easily than than a fully well-insulated building. Air control, we work on both the actual air tightness of the building envelope itself, so reducing exfiltration and infiltration as best we can. Phius has very, very stringent air tightness requirements, about 4 to 5 to 6 times tighter than the newest codes out there. We require all of our projects to have a blower door test run, and the target is very, very tight. In addition to making that building airtight, we then need to provide a fresh air outdoor mechanical ventilation system that will ensure that, because you're not getting fresh air through infiltration or exfiltration, you actually do need to provide dedicated mechanical ventilation to provide outdoor air to the occupants. All of our projects, or basically all of them, are going to also include energy or heat recovery associated with that ventilation system, so that you're not just bringing in completely unconditioned air. It's going to go through some passive heat recovery before it enters the space. The last piece, radiation control, is all related to windows and glazed doors. So making sure that you're designing for good shading and providing daylighting, so you can allow sun when you need the heat gains in the winter and reduce the solar gains in the summer when you don't necessarily want them. And then going for climate appropriate glazing is really important. So being able to manage and optimize your glazing package is a really big piece of what a lot of our projects employ. In the early 70s, mid 70s, with passive solar, there was a lot of talk about maximizing your solar gains. And you might be familiar, you might have seen projects where they've got a ton of south-facing glass with really high solar heat gain coefficients, not much shading. Those are kind of problematic in our perspective, because sure, they might work really well in the winter, but with our current climate conditions and a lot of the locations, summer is a big issue too, right? So we don't want to maximize the heating gains because you're going to actually want to mitigate those and reduce those in the summer. So we've kind of switched gears and we're talking more about optimizing and making sure that you're designing for all seasons for your building. Okay. I'm going to talk about some things to keep in mind now with detailing. So most of what I'm going to cover is related to the high performance insulation and thermal bridging elimination section, so thermal control. But the things I want to talk about at a high level, anytime you're working on a project or looking at details, in order of operation, these are the things that matter the most, right? First and foremost, structure is important. Your building needs to stay up. If your building falls down, then none of the rest of this matters. So structure is critical, of course. We as a Phius, myself as an energy modeling kind of an energy conservation group, we're not really looking at the structure. We're relying on building code and structural engineers and everybody else like that to make sure that the building is going to stay up. That's first and foremost. Um, Water control is incredibly important. So this is talking about actually like if it's raining outside, if you've got keeping groundwater away from your building, all of these pieces. This is also very important. But again, we rely on building code and some co-requisite programs to control and regulate the water control for the building. So these first two are really all things that every building should already have good structure and good water control. So we're kind of going past that and concentrating on the last three. So the air and vapor control, mitigating condensation risk, and thermal control are the main three that Phius really stands apart from regular and typical construction. And this is where our passive building principles really come in to help guide folks and lead them to better buildings that are going to do a better job of all of these pieces. So in the air and vapor control level, this is talking about where do you put your vapor retarder, how do you deal with infiltration and exfiltration, where do you place your air barrier, those kinds of things. Our certification guidebook, which I've got a link in here too, in Appendix B, has a really big section of rules of thumb and best practices for eliminating moisture and condensation and those kind of risks within your assemblies. So air and vapor control is really important, and I'll talk about those when we look at specific details in a moment here. Mitigation of condensation risk is the next one on my list here. So this is making sure that your interior surface temperature essentially doesn't reach the dew point, and you're not worried about getting mold on the inside corner at different details and different conditions. So mitigating condensation risk, we have hard requirements on this that you need to keep your interior surface temperature above the point where it could potentially have mold issues or any kind of long-term durability pieces like that. So that's a really important critical thing that happens at details as well. The most places that I'm worried about this is when you've got either really conductive materials, again, thermal bridges that pass through your building envelope and can lead to really big temperature swings at certain points and junctions in your building. And the other piece that could also lead to this is if you've got an interior climate that's really humid, right? So if you've got active dehumidification or something like that, that is going to help reduce the risk for interior moisture risk or condensation risk. The last piece I'll talk about here is thermal control. So the main things we're looking for here are to reduce our energy losses. So again, this is to kind of reduce the overall energy you're using for heating and cooling your home or your building or your, you know, office space, whatever it may be. Um, Thermal bridge mitigation and reduction is another big piece of thermal control as well. And then the last piece is comfort. So there's a difference between condensation risk temperatures and comfort temperatures. So condensation risk is usually a lot lower. The dew point is typically lower than what you're going to be comfortable with in that space. So we also have some rules related to thermal comfort within our certification program that helps manage and make sure people are comfortable inside their homes, because that's a big piece of our program in addition to energy savings and stuff like that. Okay, high level stuff out of the way. I am going to then pull up some example details. So first and foremost, I think, yeah, Twyla put a link to the Phius Project Details Library in the chat. So if I pull this up, hopefully somebody's already clicked into that and checked it out. But this is new as of, I think, like maybe a month ago or something like that. We are actively still filling out our project details library. But this is a new addition to our website where now you can go through, look at different details associated with different projects that have agreed to allow us to publish their details and, kind of show folks what it takes to get a passive building in different climates, different conditions at different points. So feel free to peruse this at your leisure. We have the first, I think, 3 projects are free to everybody. We're going to be adding more projects in the near future, and then those will be available to Phius Alliance members that I mentioned as our membership program. So example details come from this first building first. So I'm starting with a non-residential and office building project in Basalt, Colorado. I got certified a few years ago. You can also link to the actual project listing for this project, which has a little bit more information as well. It goes over things like who the project team is, measured and modeled information, stuff about the ventilation system. But so this first project is a kind of it's an interesting building. I've actually been to this site. We were able to host a CPHC training here back in 2017. So it's gorgeous views. It's in Basalt, Colorado. So the details I'm going to look at here are the first one is the foundation to wall detail of this particular project. So like many of our projects, this building has continuous insulation underneath the slab. It's got 6 inches of EPS basically under the entire slab. And then the exterior wall for this particular project is about an R59, R60 structurally insulated panel system. So I'm going to then navigate to the actual details that we were received for this one. So each of these, you can view the project as part of the details library if you're looking at the details. And then we've got a few pieces, keys, information in here for all of the views that are available. So we've got an initial hatched view, which is pretty much just the drawing set that the team gave us. And then we've taken the time to kind of go back in, consolidate, make these look consistent, and give information about the material view, an isothermal view, which I'll go into in a minute. This is kind of what we use in Therm to identify potential thermal bridges in projects. And then we spill out and pull out the air control system, the thermal control system, what the vapor control was, and any water control systems. The last piece I will note here is that in the top right, there is a legend. I think we're actively trying to fill this out more, but we've got right now the EPS rigid board is kind of flagged on this one. I think that's the main insulation material on this particular project. But first and foremost, I will start by opening kind of this material view and taking a look at what's going on in this project. So up above is the SIP panel. It did have a rain screen system out front of that SIP panel. And I keep saying SIP panel. It stands for structurally insulated panels. I should just say SIP. Sorry about that. The floor assembly itself is 4 inches of concrete with 6 inches of EPS. And you'll notice, well, I hope you can notice right away that they actually did do a pretty nice thermal break here between the concrete slab and their actual concrete foundation wall, which is holding up their walls. So the foundation wall is separated by about 1 inch of EPS at the narrowest point, and about 3 or 4 inches of EPS right below this kind of footing chunk of the slab. In addition to protect it from the exterior, which is up here in the top right, they introduced about 2 inches of EPS outboard of this slab to protect their perimeter from basically thermal intrusion here. So on the isotherm view, which I'll look at next, So this view is set up in a program called Therm. It's run by, I think it's an NROL program. But basically, this is the tool that we use to identify potential thermal bridges in a project. So you set the interior boundary condition at whatever the project is set to. You set the exterior boundary condition to outside, and then you model all of the pieces that are happening in this two-dimensional detail here. So the majority of what we want to see when we're modeling in Therm is kind of reducing pinching as much as you can in these different layers of colors. So it goes red on the inside, or red white, which is the warmest, to purple on the outside, which is the coldest temperature. And this is basically showing the static progression of temperature when it's 68 degrees Fahrenheit to whatever the outside temperature. I think we set it to 14 degrees in this particular case. So down below, you'll see there's some gradients happening because the ground is actually acting like a heat sink as well and offering a little bit of protection. But you'd be able to see pretty clearly that there is some kind of pinching happening in here. So it pinches where the insulation happens, but we can see that it's keeping it warm on the inside, which is critical. And this exterior insulation is helping keep all of the purple, dark blue outside of directly under the slab. So from a thermal perspective, this is doing pretty heavy lift with that perimeter insulation on the outside, but this interior thermal break is doing a bit of a lift as well, as you can see the difference between this light green to the red on the inside. So from a control systems perspective, I'm going to start over here on the right with the water control system, because like I talked about earlier, if you do not have water control and you get water inside your building, nobody's going to want to be in that space anyways. So in this particular project, they used a rain screen at the above grade wall and then a waterproofing membrane outboard or inboard of that. And then they've got a vapor control and water resistant layer that kind of wraps all the way underneath their slab, and then goes to the exterior on the outside of their foundation wall. So those are the main two pieces of that system that I'm going to highlight here. From a vapor control perspective, so this is a little bit misleading here. So most of the vapor control is actually from the foam, but it's kind of tough to show that in this dimension here. So the EPS insulation in this project is actually a class 2 vapor retarder in and of itself. So most of that vapor control is actually happening from the insulation, which shows up clearest on this thermal control diagram as well. So you can see most of the thermal control happens at the above grade wall, and then where it splits out underneath at the exterior, and then underneath the slab over here. So this is a pretty good example of where there is an actual thermal bridge in this project. While the conductivity of the wood isn't as high as if this was concrete or steel, this is an area that we flagged for this project, which is why we've got a isothermal view and a therm calculation. I'll come down to this linear thermal transmittance in a second here. So the last piece we've got is the air control strategy and system. So in this case, the structurally insulated panels kind of did the majority of the work, right? They did the thermal control and the air tightness control in this particular project. And then the vapor control layers underneath the slab are the other big piece. So all of these are taped and overlapped and pushed together so that this acts as the full air tightness control on this particular detail. So the linear thermal transmittance down here, this is a numerical representation of additional heat loss happening at a detail like this condition where we don't have continuous insulation lapping at the SIP. So in this particular project, the psi value did calculate as positive, which is basically showing that there's a little bit more thermal transmission loss than would be accounted for in the normal energy model. So you need to include this correction factor to account for the additional losses that happened at this condition. So in our certification program and as far as our energy modeling goes, as long as you account for linear thermal transmittance and additional heat loss like this, but you can confirm there's no risk of interior condensation and there isn't going to be any comfort concerns in that particular corner, we allow some thermal bridging and to mitigate it as best you can. In this particular project, this psi value is about 7 times the limit that we would say you wouldn't need to account for a thermal bridge. So this is a decent thermal bridge, but as you can see in this isotherm view, it's still warm on the inside edge of that concrete wall to concrete slab to wall. So there wasn't going to be any condensation risk or comfort concerns at this particular corner. We just wanted to account for the additional heat loss and the heat transfer that happened there. Okay, I'm gonna call it on this detail, and I'm gonna move on to the next one. Okay, the next detail I'm going to look at is this same exact project, but we're going to look at the exterior wall to the roof connection. So in this particular case, it's the same wall, still a SIP, and then the roof on this project was pretty beefy. They used an 11-inch SIP, and then on top of that, they introduced an additional 5.5 inches of EPS as part of the plan to get the R value that they wanted to for this pretty cold climate 6B. So I'm going to open up this detail and we'll take another quick look at what's going on here too. So similar to the last one, they all have these same views to kind of display things. So with that material view to start with, so again, the SIP wall is the same. This is the SIP up above the roof, 5.5 inches above that. And then I believe this was some fiberglass kind of sound attenuation insulation. So this wasn't doing a ton with the insulation itself, but it helped a little bit. And then again, you can see the top of this rain screen and kind of how the lapping happens at the roof with the drip edge, etc. And in this isotherm view, this is what we're looking for when we want to see kind of a continuous insulation. There's no major pinching of these different rainbow patterns that are going on here. It's pretty consistent across the board. And this is kind of representative of a good detail that's not going to have any additional heat loss that we need to account for separately when we're doing the energy model for this particular assembly. So similar to the last one, I'll pull up the water control system first. So they did have a standing seam metal roof that lapped up over the fascia, drip edge, and then back over the back half of that fascia as well to protect it from driving rain. Again, water resistant barrier on the interior, and then that rain screen on the exterior. So this is kind of a belt and suspenders system where you've got a rain screen on the outside taking the brunt of any driving rain, and then any rain that gets through is then repelled by the water resistant barrier on the face of the SIP and the fascia, etc. On the vapor control, similar to the other assembly we're looking at, the vapor control actually happens up here at the top of the roof. Again, the class 2 vapor retarders in the EPS materials are also helping with as well. And the thermal control system is basically everything that's not framing in this particular section is going to be acting as the thermal control. So again, EPS, 2 sets of SIPs on the walls and the roof, and then they've got some more insulation up above that, which they've framed out so that they can support their standing seam metal roof. Last piece is the air control system. So the outer face of this SIP was taped, and that was basically the main air barrier on this particular assembly. So linear thermal transmittance, we did the therm calculation for this one as well. And the psi value, which is essentially the adjustment factor for if it's positive, that means there's more heat loss. If it's negative, that means you've actually got a thermal bridge that you've accounted for all of the losses properly. And it's actually saying that, you know what, this actually uses less energy than what the model would assume it would. So we don't necessarily take credit for negative thermal bridges. It's just a bonus that the team has done a good job of detailing this particular juncture. Okay, so that's a pretty decently cold climate, climate zone 6B, which is cool and dry. The next project we're going to look at is in Olympia, Washington. This one is for a single family home in a mixed marine climate up in the Pacific Northwest. Also a little bit older. It's a Phius Plus 2015 project from a few years ago. Similar to the last one, we do have a page that's got more information. I think they had some more pictures as well. This is a pretty nice single family home. And so they've got all this good information about who with project details and where it's constructed and stuff like that. So feel free to peruse our project database as well. And the first detail we're going to look at here. So again, slightly warmer climate. It's climate zone 4 instead of 6. And this is a single family home rather than an office building. So in this particular foundation to wall, we've got an R28 slab on grade with 6 inches of EPS, and the exterior wall is about R45. And they actually did a framed stud wall with continuous insulation outboard of that. So in this particular assembly, it's a little bit different than the last one. They're not just using, SIPs. They actually did a framed wall assembly essentially. So in this material view, you can see they've got a framed wall assembly above with continuous insulation outboard. They've got kind of a different situation. They don't have a thermal break between their slab and their concrete kind of footer beam, grade beam piece here. But they do have continuous insulation all the way around this particular detail, which is not necessarily going to work in every climate. For this particular project, they actually have pretty bad soil. So the entire building is on a pier and beam system. So they've actually got pylons, I think, spaced about every 6 to 10 feet apart, going around the entire perimeter of this building that they had to drive pretty deep to hit bedrock. So everywhere there is not a pylon, they have continuous insulation outside of this grade beam piece here. Similar to the last one, they do have a rain screen outboard of their continuous insulation, but it's quite different in this particular climate and for a project of this size. So again, on the isotherm view, we have pretty decent. It is pinched here, right? Because you got less thick of insulation at this juncture than you do up above, but it doesn't have the same, sill plate going all the way from the inside to the outside of the detail. So in this particular case, I believe this thermal bridge calculated as negative as well, because they've got pretty good consistency in their isotherms here. Okay, so like the last one. So again, rain screen is doing the heavy lifting, and then they got a water resistant barrier outboard of that. Underneath their slab itself is where their water resistant membrane is on this particular project. It also acts as the vapor retarder in this particular project as well. Um, and then if we look at the thermal control, you can see this is much more continuous. So they've got cavity insulation, and then that 6 inches of EPS, 4 inches on the perimeter, and then another 6 inches below the entire slab as well. So this one, if I was drawing this and trying to trace the thermal envelope with my pen, I would not have to pick up my pen to kind of show the entire thermal envelope going continuously around that entire footing, which is what we want. That's a good thing. The air control system in this particular project was the sheathing in between the framed assembly and the exterior insulation. So this wraps and is taped underneath the sill plate, which then meets the vapor retarder underneath the slab. So this entire air barrier is made of 2 separate materials and then taped to get in between them, because we have a class 1 vapor retarder underneath this slab that connects to essentially a plywood or an OSB. I think this one was actually plywood, if I remember correctly. Okay, so linear thermal transmittance. Okay, I was wrong. This one is also slightly positive again because of that pinching. But this one is only about 4 times higher than our limit of what we would ask project teams to count for with additional heat transfer at that perimeter. So small price to pay, and similar to the last one, it's very warm on this interior corner, so we don't have any risk of condensation at this plane, and we don't have any comfort concerns either. Okay. The next detail I have for this project is a window header. So window detailing is also critical on all of our projects. We want to make sure that you're using really good high performance windows, installing them correctly and leaving yourself room to account for everything here. So in this particular one, it's the same wall as the one we just looked at. So it's still that exterior wall with the 2x6 fiberglass and the 6 inches of continuous insulation. The windows in this particular project, they were using Zola thermoclads. I think it's a European manufacturer. This is also quite an old project, so we didn't have many American manufacturers at that point making triple pane windows like this. But it's a very high performance window, and the installation detail is what we're going to look at next. Okay. So we've got the material view showing here where we're showing the generic window assembly here, showing what's happening. We've got backer rod and sealant up above. They've actually taken a little bit of a good approach here that we see consistently on our projects, especially single family homes, where they're actually doing what we call over insulating a window. So the entire front frame is not actually shown in the in the assembly here. You actually are going a little bit past it, providing a little bit more insulation outboard to help protect this backer rod and sealant, which is an area that can have pretty decent thermal transmittance through because it's not as much insulation. You've got a lot more framing on this back end to help support the header above the window. And then they've got their soffit piece directly outboard of that so that they have a nice finish basically to look at from the exterior. This one also has a rain screen as well. And then the framing, etc., happens inboard of all of that, kind of directly above the window. The other good thing about this placement of this particular window compared to a typical building or projects that you might see, this one is very centered within the wall assembly. So it's trying to line it up right with this air barrier, which is the sheathing here. Many projects that I've seen that kind of struggle with detailing and projects that I see just walking around city of Chicago or I mean basically anywhere, you'll see windows pushed all the way to the exterior. Those are typically flange windows. You'll see some windows pushed all the way to the interior. Center of the wall really performs the best in terms of thermal performance of the assembly. From a water management and a structural perspective, you'll definitely need to go through and make sure that that works first before you can start to look at the thermal performance. But this one is well aligned with the structure above, and the sheathing made a pretty good ability for this window to be well air sealed as well as be over insulated up here at the header. So in the isotherm view, so you can see really consistent wall up above, and then it starts to distort once we get to the actual window itself. So again, the windows are the weakest areas in any building. They usually don't perform as well as the typical wall. It's just thinner, doesn't have the same R value, doesn't have the same resistance to thermal conductivity. So this one you can see it kind of pinches as well. But that's again because we're going from a really robust thick wall assembly down to a thinner, not as thermally performance good assembly down below. So this pinches. This is expected basically on any project, but again we've got really good thermal temperature. Conductivity is not an issue. There's no major thermal bridging happening, even though they've got some framing and the window itself. So this is a really good detail as far as window installation goes. From a water control perspective, so rain screen with the water resistant barrier behind is typical. And then the window itself is essentially acting as our water control system. It's the air tightness layer, it's the insulation, it's all of those pieces when we look at this overall. So maybe I'll focus on the air control one because that one's a good one to keep in mind. So again, it's I think it's OSB in this particular project that's taped. All the seams are taped. It gets taped to this piece of plywood or whatever this chunk is here. That then extends around to the backer rod. The window itself is then taped to all those pieces to provide a really continuous air barrier at the window detail and installation itself. Okay. And then from a linear thermal transmittance perspective. So our psi value on this one calculated as 0.009. So this is really, really good. Our limit where we say, okay, you don't have to worry about thermal bridging anymore is 0.006. So this is only 3/1000ths of a BTU per hour foot squared off of our of what we're looking at here. So this is a really, really good window install, and performed super well from a thermal perspective. I do see there is a question in the chat, which I will try to address real quick because we're still on the same project. Looks like, are we accounting? Yeah, Dennis asks, are we accounting for the compressive strength of the rigid insulation below a footing or a slab? Is there concern for settlement? So in this particular project, they were not concerned with the settlement issue because this grade beam is basically acting as an actual beam, and then they've got um, piers every 6 to 10 feet going around the entire perimeter of this one. So I don't think they ended up, yeah, they didn't have any concern for settlement. It's a built project, and the structural engineer signed off on the compressive strength of the rigid insulation here. Okay, and then the other question Dennis had, what are the precautions with fasteners breaking the thermal bridging? Okay, so yeah, this particular project, it does have fasteners in it. Like, you have to hold up the continuous insulation somehow. But in this particular project, they use thermally broken fasteners. So I believe they are some kind of a plastic material, essentially, that help reduce any thermal bridging created by regular fasteners. But on projects that don't go for thermally broken fasteners, or they're using, just regular clips or regular, mild steel fasteners, stuff like that, we do ask project teams to account for the reduction in the effective R value of the continuous insulation when you've got fasteners that are penetrating your exterior rigid insulation board. Okay. The next project that we're going to take a look at is a project in Wakefield, Rhode Island. This is another single family, and this is kind of an in-between climate zone. So 4C is a little bit more mild. It's a mixed climate zone, especially the marine areas there. This is Chicago's climate zone. This is a big swath, big chunk of the United States, climate zone 5A. And this project number, again, another Phius Plus 2015 project. We were able to get permission from older projects first for as far as the detailing goes. But this is again another big single family home that we certified quite a while ago. Again, more information about who worked on the project, project team, etc., building owner, and the construction team. So this particular project, I've got, I think, another 2 details to look at. And this one, we've got another foundation to wall. In this particular case, this project had a basement. So the basement wall to basement slab is the detail I think I've got highlighted here to look at. So this one also has 6 inches of EPS below the basement slab. The basement wall itself was essentially a double stud wall, but the last cavity of this wall, they applied closed cell spray foam to. So it's a 2x4 wall assembly with a 4.5-inch gap that was also filled with fiberglass. And then they've got another, basically 2 passes of closed cell spray foam were used on this particular project to ensure that it had continuous insulation that had vapor control between the slab, or the ground, the foundation wall, and the slab itself. So this project, similar to the other ones, I've got a zoomed in detail here. So they've got a, oh, this one, the other reason this one was interesting, why I flagged it. This one has a concreteless slab, which is fascinating to me. We haven't seen a ton of these. This is one of the first ones we saw. So they've essentially got just 2 layers of 3/4-inch plywood is acting as their floor slab with their finished floor above. The 6 inches of high compressive foam EPS below it to kind of keep it from settling. But they've got then that 2x4 wall above, which is not really doing anything structurally. This is just holding up the sheathing, holding up the interior gypsum board, and making sure that you got enough insulation in this exterior wall. And then they've got the closed cell spray foam, which essentially touches the EPS and then journeys up the extent of the interior of that wall. They've got their footing with a drain tile right next to that, essentially. So in the isotherm view, which this is a little, oh, I can zoom on these. Okay, cool. So in this bottom corner here, the isotherms are pretty good. It's not too pinched. It has a little bit of waviness, and then it comes all the way up to where it extends to the above grade wall above and the rim joist, which also has some closed cell insulation inside of it too. So this is a pretty big kind of section we had to account for here when doing this thermal bridge, because it's got a lot of different pieces that are really highly conductive on this concrete foundation wall. So from a water control perspective, similar to the other below grade piece we had, water control is mainly in the outboard of this. And then they've got vapor control and water control directly under that slab here. So the vapor control system, they do have closed cell spray foam. They've also got membrane underneath their entire piece. And the foam itself, again, is, I believe this is EPS. This one was, yeah, it's EPS on this one, I think. I think the legend might be off. So they also got foam insulation underneath, which is acting as a good vapor control layer as well. And then the thermal control is insulation all the way around the entire perimeter here. And in this case, there's not even any highly conductive concrete to really bridge this too much either. From a linear thermal transience perspective, this one calculated as negative. So this one is performing better than what our normal energy model is seeing, just from overlapping assemblies. So this is a pretty robust detail, all things considered. We have not heard any issues from this project team on having a concreteless slab in this particular project, which is great. Okay. And then the next detail I've got for this project is the wall to the roof. So it has the same kind of exterior wall. It just doesn't have the concrete for the above grade portion. It's essentially another kind of a double wall stud or a double stud wall that's got fiberglass fill on the interior with another 4.5-inch fiberglass layer. And then they closed cell spray foam the exterior to increase the um, basically the interior temperature a little bit and make this assembly more robust. The roof itself is a blown-in cellulose kind of vented roof assembly. So take a quick look at this assembly as well. So starting from the top here, it does have a vented soffit and then vent 1.5-inch vent gap with baffles above the cellulose insulation here. All of that's held up by the regular roof assembly below, and the trusses are within that. The double stud wall here, which has got the closed cell spray foam on the exterior and the fiberglass on the interior, like we just looked at. From an isotherm view, this one also performs pretty well. It's got a little bit of a pinch here, right, where there's a exterior framing happening, but overall, it's not too bad in terms of the isotherms. It's, again, warm on the interior, not worried about condensation risk or comfort concerns. For the water control system perspective, this one, I believe, let me see. Do I have a picture of the actual roof? I don't remember what this roof is. I think it's a shingle roof. I don't think this one's a metal roof. So I think this one has shingles, and so that is the water control system and everything like that. They've got the soffit and then rain screen outboard of their double stud wall for most of the water control. And in terms of vapor control, most of the control at the roof level actually happens in here. The sheathing underneath the trusses acts as their vapor control, and then they've got a vented vented air gap above to allow the roof to dry to the exterior. Is the goal of this one. Their thermal control again is the cellulose plus the wall assembly, and the thermal transmittance of this one also calculated as negative. So it's a pretty good assembly in terms of thermal performance. Okay. think I'm just about wrapped up, and I do want to leave some time for questions. I don't remember if I have any more slides left. But I do see there are a couple more questions in the chat. So I'll hit those first and then maybe open it up for full questions. Okay, question, is Phius working with PHN to build a more robust detail library and share resources? It's my understanding PHN deals with climate-specific recommendations somewhat. I don't think we're working with them actively right now. We've got enough work just like getting details from our own projects to get into this library. This thing's been about 3 years in the works. So not to my knowledge. I don't think we've got anything lined up with them at this point. And then there's another question. Okay. Under what climate conditions would concrete be a positive feature as in acting like a heat sink? It's a good question. I mean, thermal mass is important on projects in almost any climate, like being able to adjust the interior conditions and being able to store some heat in an assembly and then have it radiate back later. I would say mostly probably the really hot climates are going to be the best places, though, that, just having an uninsulated slab or something like that would be uh, a positive thing to do to help with the heat control of the project. Um, yeah, but I mean, there's a lot of things besides just using concrete as a heat sink to consider. I think there's global warming potential with concrete that's just inherent. Like I wouldn't do concrete unless you needed it from a structural perspective in most projects. You can use other materials as a heat sink as well, like interior gypsum wallboard, if it's thick enough, can act as a heat sink. Just leaving some spaces uninsulated can act as a heat sink. Most of our projects, and especially these 4 projects, are in a little bit colder climates. They're not necessarily worried about the cooling period as much as they are the heating period in these particular details. It is a good question. Okay. Oh, I do have question time now. Excellent. All right. I saved just enough time for maybe 5-6 minutes of questions.
Awesome. Thank you, James. For those attendees that want to ask questions, you can either raise your hand and we can unmute you if you'd like to ask a longer question to James, or put it in the chat as people have been doing throughout. Either is okay. So feel free to do either of those at this time. James, you just did such a good job going through all these details. People don't have questions. I love it.
That's fine. I mean, yeah, we see a lot of different detail types, and we are, again, this is a brand new thing to our website, so we are going to actively be adding more details from projects we have certified. This next batch, I'm hoping, is going to be a little bit newer. Not the 10-year-old projects. Maybe we can get some projects that last 3 to 4 years would be ideal from my perspective. But yeah, it's there. We're working on it, and I'm hoping there's going to be more soon.
Great. Well, if we don't have any more questions, feel free. Oh, sounds like we got a few in the chat. Also, we've linked a feedback survey if anyone wants to give our feedback. Maria has raised her hand, so I'm going to unmute her first, and then you can get to the chat.
Sure.
Hi, James and everybody. Maria with SGH. My question is the intent with the detail library that one day if you find a detail, say that you want to use that already has a therm model made, that maybe you could say, I'd like to use this detail with this therm model and I don't have to do it for my specific project?
It's a great question. I don't know if we've thought that far ahead. I think the first goal of the details library as a whole was just to give people more starting points, I think, in terms of like initial design. We weren't really thinking about it from like we've modeled this in Therm and then you can use that detail kind of thing. We're not trying to do necessarily like the RDH details library or the what's the other one? Gosh, I'm blanking on the name, but there's another big group out of the Pacific Northwest that has a details library as well. We weren't really thinking about it from that perspective. But if you happen to have, an exactly identical detail, I think we would allow that to be used for sure.
Okay, that makes sense. Thank you.
Yeah, thank you for your question. Okay. I do see one from Nate. How long does it take to get the details uploaded from a project into our, I'm assuming this is into our details library. Well, for these ones, it was 10 years. So I'm hoping the next batch is going to be a lot shorter. I don't have a great answer for you, Nate. Basically, as soon as we can get permission from a project team, and if it's a newer project, we would try to get that in a lot sooner than these guys. We now have all of our templates figured out for how these all are going to look and be consistent and have similar information. So that was a big chunk of work. And now basically it's just a matter of, having staff time to be able to pull that information in. Okay, and then I see one more detail related one from Steven. Have any projects completed a pre-installation blower door test to confirm the envelope robustness prior to covering up with the gypsum board? Yes. I think in general, most projects, I mean, we always recommend you do a pre-cover up blower door test. I think this is very common on most of our projects to do a pre-installation blower door test or like a mid-construction blower door test to make sure that the project's on the right track. Yeah, if you just did a final one and we're hoping for the best after the JIP went up, you'd probably be in a world of hurt in some areas because you wouldn't be able to track down the leaks. So yeah, definitely recommended. Many teams do that. Okay.
Gary, I can't tell if you're raising your hand visually or if you're just stretching. I just wanted to double check. Happy to unmute you if you are just stretching or have a question.
I think he's good.
Okay. All right. Okay. I think that's everybody. And James, we're almost at time, so I'm happy to wrap up a few minutes early. Thank you so much for taking the time with us today, and thank you for everyone here. We're really excited about this detail library and sharing it with everyone. So thanks again, and we'll talk to you later. Bye.
Thanks all.